Hello and welcome, you gloriously curious quantum cadets, to another enthralling episode of Impact Quantum, the podcast where we decode the mysterious and often misunderstood world of quantum computing, so you don't have to have a PhD. But it certainly doesn't hurt. In fact, today's guest does have one, so we're fully covered on that front. I'm Bailey, your semisentient host, stitched together from sarcasm, superconductors, and a few well-placed qubits. I'll be guiding you through today's conversation, one part science, one part curiosity, and possibly several parts existential dread if we stare too long into the quantum abyss. Joining our dynamic duo of Frank Larvine and Candace Gilhooly is the marvelously multi-talented Kevin Villegas Rosales, Princeton PhD, physicist, and customer success sorcerer at Quantum Machines. Kevin breaks down what it actually means to work in customer success when your customers are wielding quantum hardware. Spoiler alert, it's a bit more complicated than resetting a router. We'll dive into Kevin's journey from condensed matter physics to the world of quantum computing, explore common misconceptions, tackle the intersection of AI and quantum, yes, that hype train, and unpack what it takes to make quantum tech usable by mere mortals. So grab your Schrodinger's snacks, fire up your favorite entanglement simulator, and let's get quantum curious. Now, over to Frank and Candace to kick things off.
Hello and welcome back to Impact Quantum, the podcast where we explore the emerging marketplace and industry that is quantum computing. And you don't need to have a PhD, although it does help. And I think our guest today does have a PhD, but you just have to be curious. And with that, I have the most quantum curious person I know, Candace Gilhooly. How's it going, Candace?
It's going great, Frank. Thank you so much. I'm really excited about today. We're going to be speaking with a gentleman named Kevin Villegas, who is actually a Princeton PhD, so he checks the box there. And he is the team lead and a customer success engineer at Quantum Machines. So hi, Kevin. How are you doing today?
Hello. Good morning. I'm doing very well. Thank you so much for the invitation.
Awesome. So what does customer success mean in quantum space, right? Because, CSEs, CSAs, whatever you want to call it, different companies call it different things. What does that mean? Like you obviously, so as I understand it, customer success engineers are generally people that once they buy something, you go in there to help make sure they're successful with it. Is that the case here?
Yeah, very good question. I also have heard CSM, Customer Success Manager, in some other industries. This is an extremely good question. You know, when I graduated from Princeton back in 2021, I started to do my job search, and I was really keen about going to industry. So I had my degree in physics, so I wanted to do a continuation of that. Most of the jobs that I found at that time and applied for were related to research and development in the quantum industry. Because that's where things are right now, right? You know, we're in the development of quantum computers. There has been some applications being demonstrated, but nothing like is fully, that we have it on an everyday usage. So, but then I stumbled upon Quantum Machines as an opportunity, actually through a friend in my department, and there was an open application. And after the interviews were completed and everything was successful, I understood that I was going to be part of the customer success team, playing the role as a physicist. So what customer success means to us is, advocating for our customers and helping them achieve their goals. Whatever that definition is. So, we work with universities, startups, companies, and each of them have different goals. So we want to advocate for the correct usage of our products into their application. This can be broken down first in an onboarding, in which we train them with our technology. We want them to become independent, but we want them to be trained and onboarded in a very efficient way that makes them be up to speed very quickly. And also, very soon after they receive the instruments that they purchase, we want them to be able to execute the application that they have dreamed of, at least in the very near term. And then we have like ongoing conversations, communications, and consultations with them to make sure that they're getting the most out of what they have, acquire when they start to think about working with quantum machines. So it's a little bit of what it means on a very general point of view to us.
Interesting.
Okay, that is interesting. Well, I want to just take a little step back for a moment, and I want to start with the beginning of your journey and what sparked your interest in quantum computing.
Wow. Yeah, this is a great question. I really like to give an answer to this question because to me it actually started before quantum computing. I'll just give a very brief sentences about that, and then I'll get into quantum computing. You know, I did undergrad in physics, and to me, when I started, I know it's way more complex than this, but to me, it was divided into like you either study things that are outside of the Earth, galaxies and stars, or you study things that are, very small and tiny and behave very differently. So my attraction was to study the very small things, so nanoscale, microscopic, studies. That was what was my interest. So I took that decision to pursue that. Now, quantum mechanics is applied in both cases, actually. So it's not that you only like face quantum mechanics when you do very small scale things. There are also quantum mechanics in the macroscopic things. In some scenarios. So I took that path, and then undergrad is in physics is a very general education. You learn about many fields, and usually the specialization comes in the PhD degree. So I was very familiar with nanoscale devices and whatnot, so that was what I decided to pursue further. I did the studies in what's called experimental condensed matter physics, which is in the realm of quantum physics and quantum mechanics, but not exactly quantum computation yet. And I will connect the dots in a second. So I was studying the properties of what we call macroscopic quantum phenomena, which means that it's something that is at the scales of what humans can interact with. The samples that I studied were, millimeter size, even centimeter size crystals that were grown in the university. And we study, like, for example, resistance and voltages that were driven through these devices. And while they were like showing a behavior that cannot be described by like everyday physics, so we call it like emergent phenomena in quantum mechanics. So we were studying that, and it is in an area called many body physics, which is to say that when you have like billions of particles interacting together, the particles can be electrons, the particles can be also like atoms, they do happen to behave in an unpredicted, very different way as if you were to be looking at just a single electron, for example. So I was studying many body physics. It was something very interesting, but here is where it changed for me. So I was studying voltages and resistances of these macroscopic states that only happens after billions of electrons, interact with each other. But we only see this as like the outcome of their whole interaction. So at the end of my PhD, I was really curious to understand, like, okay, what if we start from the other end? What if we were able to manipulate, one electron or a few electrons and then putting them all together and then see how, as you grow the system size, they happen to exhibit this like emergence phenomena. And there are a few approaches to do this. And the one that interested me the most was the one that you could pursue with quantum computation. And that is because, we have the one qubit that you can fabricate, and you can put a few more qubits, and then you can make them, you can control them and make them interact and behave like electrons. And then you could see how the physics happens when you put them all together. But what was unique for me is that usually in quantum computer, regardless of the platform, meaning superconducting or atoms, for example, you can address the qubits individually. So at the same time that you can put many of them together to see an emergent phenomena, you could still have the tool to study what's happening on each of them individually. And that was the curiosity that drove me to this field, actually.
That's amazing. There's a lot to unpack there. One of the things you said early on was you wanted to go into industry.
That's right.
Were you thinking about quantum computing when you made that decision, when you were like, I want to go into industry, I want to go into quantum computing, or were you thinking about some other career options for quantum physics in industry?
Yeah, thanks, Frank. It took a tour, my decision. So I think it was fifth year on my PhD, and I said like, there is a moment in your PhD after you're so many years in the laboratory, really focus when you like, you let's say lift your head and you realize, oh, it's many years past. What do we do next? And I concluded that I wanted to pursue industry, so no more, let's say, university-related endeavors. And at the beginning, it was like, okay, so many years of physics, let's do something different. So I started to investigate what can a PhD, in physics could do. And there were a few different options. There was possibilities to do software related work. There was possibilities to do financial related work. There were definitely positions in research and development and in like, for example, semiconductor industry, materials research. That are industries that are very mature, I would say. I'm talking about software, finance, R&D as well. So I took my time to think and consider, and then after a few months investigation of what were the options, I actually concluded that I still wanted to use my studies in quantum physics for my next position. So I kind of said like, okay, not really, not the other path, not the software part, not the financial path. Let's try to do quantum. By the time I started in Princeton, which was 2015, it was just 1 year before IBM started to make very noticeable advancements in quantum computing. So throughout my PhD time, I was able to see how it became more and more important. IBM, Google, and then all these other small very important players started to make a dent. So it became obvious that there was something going on with quantum computing. And then they were looking for PhDs with some quantum education, and I was able to prepare myself for interviews, very important, and then close the gap. And at the end, I was really happy to be employed by Quantum Machines at that time, getting an offer. Yeah.
Very cool.
So I can, I'm listening to you explain, you're known for being able to explain quantum concepts in clear and creative ways. What's one misconception about quantum computing that you would like to debunk?
I see. Let me think for a little bit. Yes. So I believe I know what I want to talk about. A few years ago, I've been like about 4 years now with Quantum Machines as a physicist in the customer success team. It's something I do really truly enjoy being as part of being a physicist, but working with customers actually and serving them. Okay, so a few years ago, I travel for my work a lot. To do customer work most of the time happens on the customer side. So I go to visit customers, and then when I visit customers, sometimes other members of the company join me, not necessarily from my team. And then we get to chat, right? And then you're in a room with people from different backgrounds. Some of them don't have a background in science and technology. They come from other areas like marketing and sales, for example. To make a company, it requires a team of people of diverse skills to make it work. And then I always, there is a lot of excitement for quantum computing. That's why we all decided to be employed at a quantum computing company. But I always thought that there was a little bit of a when you talk about what does it mean to have a quantum computer, right? So
Right.
I was telling my colleagues in other departments, not the technology ones, that their cell phones, the laptops that we have, they're all working with, quantum principles. Like the fact that we have the transistor, the semiconductor industry, like it wouldn't be possible to make electronics we have right now without the understanding of quantum mechanics and how does it emerge in semiconductor. Like the fact that we have energy bands and gaps in the energy bands, and that leads to the capability to turn on and off a transistor. All of these, they cannot be explained with classical mechanics. They have to be explained by quantum mechanics. It's an emergent phenomenon of semiconductors. So because of that, I used to tell just kind of joking a little bit, it's like, well, your cell phone, it's a very strong quantum computer. As I was stretching the usage of the word. But yeah, so what I want to say is that, a lot of the technology that we use in our computers and every day, all of that has a lot of quantum mechanics of it. It is the quantum mechanics leads to their behavior that we can use to use our cell phones and laptops today. Where the subtlety comes from is that we don't do the computation using the laws of quantum mechanics. You use the computation using the classical information, which is just, a qubit can be, no, sorry, a bit can be 0 or 1, but cannot be a superposition, right? So yes, we process classical information with hardware that has emergent quantum physics behavior. So that was very important for me to kind of understand and spread it around, actually. So I really enjoyed this subtlety, actually.
Interesting.
Yeah.
Interesting. You said a lot there. I mean, one of our big theses for the show is the idea that, you're going to need more than just quantum physicists to make a successful company in the quantum industry, right? Neither one of us has a background. I have a cool T-shirt that you can buy on Amazon from us, but it's one of those things where you're going to need a lot of diverse skill sets. And, what would you say to someone who's not a physicist? Well, two questions for you. One, what would you say to someone who is at university today, who was in the sciences? What would you recommend them to pursue in their studies for the career? And someone who was not in the sciences, right? In this. And I know that's a small question with some big answers, but because I think you're one of the few people that I've spoken to, I'm sure you're not the only one, that has made a very conscious decision to go to industry with a PhD in quantum physics. Most of them tend to want to stay in academia for reasons, many and valid. But what makes me fascinated with your story is the fact that you consciously said, I want to go to industry. And I think that the timing of this, again, IBM always comes into the conversation when we talk about quantum computing, right? So I mean, they really are the elephant in the room. Yeah. So what would you tell someone who is in sciences and not science and outside sciences?
Yeah, that's a very good question. So let me start by telling a little bit of a story of something that I found within Quantum Machines, right? So Quantum Machines is a company that we sell products to different people who want to do their quantum computing, quantum information application. And, we have a product, and the product is primarily built by engineers, to be honest, not really physicists. So there is a lot of doing it together, actually, rather than just a physicist doing it. And where is the story coming from? There is an R&D department in quantum machines. There is engineers for hardware development. There is engineers for software development. And I was browsing on LinkedIn the other day and found a post of a colleague who is part of the software team, and he's hiring for his team. He's hiring software engineers, and he's making some little posts to debunk that you don't need to be a physicist to work for a quantum computing company. And what he was, and he's like making some small cartoons here and there, and the message was like, this is why we don't need all physicists to make a company. And it had to do with, yes, there's we have physicists in the company, but it is about working together and not just the physicists doing it all. We still need very skilled and talented software engineers that are going to solve these like 3 problems that are like pure software engineer problems. And, it is just a combination of the conversation of a very talented software or hardware engineer with like the context knowledge of the physics that is going to make the final product, actually. And that to me was really important because as a physicist, I am very good at understanding, the quantum or the application, but I cannot program an FPGA. I cannot do very well software coding. And it is the working together what makes it successful at the end. So you do need beyond physicists. And then going back to your question, Frank, about, what would you recommend to a person in STEM or not in STEM, right? So I would say that there are multiple stages to join quantum computing field. There is the R&D stage, and there is the making it a company stage. So if you want to join an effort of building like a quantum computing chip or building the algorithm that is going to be used by a quantum computer, those at this moment require very specialized skills. Usually I would say a PhD education. So it's like, okay, you do your undergrad in in STEM, and then you pursue further computer science, math, or physics, or chemistry. In relation to quantum computing, you work with a professor who is in the area making relevant publications, and that's how you become up to speed and in the frontier of that area. And then you join a very specialized company, which are very few right now who are only solely focused on the R&D and the development. So, but that is if the person wants to pursue that R&D and development. If you're not part of or not have too much interest on that part, like you can pursue either technical or not technical degree. And I would encourage the person to look at the companies who are a little bit beyond the research and development of the quantum computer, but the ones who are trying to make a company or a business out of it. Like, there is a lot of desire to have the quantum computer ready, and it's extremely important. But not all companies are trying to make an immediate revenue that year. So it would be important to understand which ones are the companies or players that are interested in yearly revenue, because those are the ones who need software engineers, marketing people, salespeople, and all of these different diverse skill sets that will also include physicists. But it's a little bit more diversified. Yeah.
Okay. So let me ask you, we often hear both hype and doom about quantum. How do you personally separate realistic progress from marketing noise?
Yes, this is very, very challenging. And I think, so I can tell you a little bit of my experience, and then I will go to a little bit of a general answer. Being first, so I had an education in quantum physics, and then I decided to do industry in quantum computing. So because of this, I have I continue to be up to date with what happens in the research and the universities and companies, so I can distinguish very easily, what is the scientific product and what is the story surrounding the scientific product. So that's where I sit. So for me, it's easy to understand. Okay, so if I read this is the scientific product and this is the story. So is it easy for me to digest? But I can imagine this not being so easy if you're not in a position where I am. So I would say that here, what I would recommend is you don't need a PhD for this, but it's a little bit of the scientific approach where you kind of read first, don't take it as face value and admit that it's a complete truth, but do follow up. If there is a message or a notification that has a purpose of marketing, which it exists as a purpose, it has a self-contained maybe 300 words message. You can always try to understand where is that coming from and see where that takes you. So I personally don't want to condemn small messages or marketing or anything like that, but you need to read it. You need to understand where is it coming from. Then you go to the source, and maybe behind that there is a scientific publication or not. So, but it's just about following up and doing the investigation of the information, and that will help you making the difference between what is the hype and what's not the hype, rather than just reading something once and saying okay, this must be true or this must be a lie. That's what I would recommend to help ourselves on the debunking.
Okay. So if someone wants to experiment today, what platforms or tools would you recommend for some hands-on learning with real quantum hardware or simulators?
Yes, this is a very subtle question. I will give you a little bit of my perspective. So, not when a person who has interest in this field that is not next to a quantum computer, for example, if let's talk about IBM. IBM have quantum computer deployed and they have offering through cloud, right? if the person who has interest in learning is not like an engineer or a scientist on the premises where the quantum computer is, it's going to have a different learning from the person who is on site. So we have a small group of people who next to be to the dilution refrigerator, to the vacuum chamber, who can see and do the experiment with lasers and microwave signal to do the manipulation of the quantum computer. Okay, so that's one type of learning, and this is not accessible to everyone, unfortunately. It may not be actually of interest to everyone, actually, because these days the three of us could write a Python program in our laptops. We don't need to go to the chip and understand how the transistors work to make this programming work to us, actually, right? So I just described the case of like working very closely to the transistor, but may not be interested to everybody. And then we have what comes out to the content that everybody can get access to, right? So that's simulators. There are services, companies like IBM or Microsoft through cloud service. They give you access to either a simulator or the hardware that companies are offering. I personally didn't do too much of this side of the studies, but I have seen out there, like, IBM has some offerings that I believe are even like had some period of time for being free. And then Microsoft Cloud Services has access to different hardware systems that you can get some time on them. And then these correspondent companies happen to have tutorials attached to them, and these things. This is the way that one can learn. Yes, but it's a bit challenging, I have to admit, because it's not fully developed, the quantum computer, yet. So it's not clear that what we learned today is something that will be relevant in a year from now, because it's just evolving really fast.
It's interesting how that's become a theme in technology, right? Like whether
Yes.
it's AI and quantum, right? And I always joke, like, keeping ahead of what's happening is become what used to be a part-time job. Now it's almost a full-time job. And I think at some point it might flip and even be there's just so much happening in both those spaces. And I mean, at some point it's exciting, but at some point it's a little exhausting too, right? Like last year I went on vacation at a place where there was the Airbnb host said that there was Wi-Fi or internet, but there really was no connections. So it was kind of a mixed bag, right? Because like it was nice to be disconnected, but we don't realize like how much of our world is shaped through internet connection. But yeah, no, that's a good point. It is moving very fast, and
That's right.
I can't imagine like just what it would like to be like a student learning this stuff today, right? Now, some of the fundamentals don't change that often, but still, like it, like you said, like there's no what is going to be the quote unquote winning technology for a quantum computer is not exactly clear just yet, right? And there certainly are a lot of players in the space, but there, again, there's no guarantee that one of them is going to win. But obviously, I think there's certain, quantum information theory tactics are going to be mostly the same, right? And I don't think there's going to be any surprises, in at least not right away, in the types of problems that quantum computers will solve. And I think that's one good antidote to hype, right? It's not going to solve everything, but just things that have been very difficult for conventional or classical computers to solve.
That's right.
Right. We've been talking about, I know Frank and I have been talking a lot lately about classical computing and quantum computing and where's the bridge, and how quantum is not going to replace classical computing, because the classical computing is relevant and optimal for certain answers that we need. So there's no reason, quantum is not there to figure out spreadsheets, and it's not there to figure out web browsing. Like it doesn't have to. So that's why there'll always be a place for it. But I wonder, since we've talked about the importance of understanding classical computing first, what does your classical background, how does it help you navigate the quantum world?
Yes. So yeah, I think this question goes back to Frank mentioned about the fundamentals. Yes. So right now it's all about development of the quantum computer, and there are some algorithms that have been proposed that can be solved with quantum computers, and we're still on the path to answer that question. Um, how do you how do you how does a person with some education can tackle this always changing information flux and things being updated? So I would say that the courses that the most I have used and the knowledge, the education that has been the classical education I have used the most is just the fundamentals of quantum mechanics and statistical mechanics and solid state physics. And the fact that I took those courses and went through the action of doing the problem set not only gave me the fundamentals, but also the ability to digest the problem and be patient and don't give up too easily, so that I can reuse this. Be patient with the problem, read it very well, don't give up too easily. Look for the sources, and that is what led me to then try to understand whatever new content is coming out actually. And yeah, I think the fundamental or classical education of just physics that was discovered 100 years ago and so on, it's still very relevant to catch up with the new things on my field of study.
Okay. I find that there's a lot of buzz going on around the intersection of quantum and AI. Do you think the hype is justified? Where do you see the real synergy happening?
Yes, I read about this a while ago. I was not up to date recently, but I think if you look at the technical terms, what I understood back in the time is that I'm not exactly sure for AI, but it was for machine learning. I believe there is a lot of matrix multiplication that has to happen for it to work, right?
Yeah.
And then the laws of quantum mechanics can be described by a field called linear algebra, and that's where like the matrices are. And so it seemed very natural that if you could encode information in quantum computers, and that the evolution of the quantum behavior happens through the description of matrices, it would seem natural that this synergy of linear algebra in the laws of quantum mechanics and the fact that machine learning and related fields use matrices so much, it seems that there must be something there, right? Like it cannot be just by chance that these two things are so closely described. So I think there was a point in time a couple of years ago where we're talking about quantum machine learning, where like matrix multiplication on quantum computers and the nature itself doing the matrix multiplication. So I think there was a connection to that and a little bit of a hype for that. And I think one thing that is happening is maybe they become a little bit disconnected now, actually. Like generative AI and AI models have become so powerful in what they want to do with their like computational power, meaning like discovery of proteins, for example. They tackle that problem with their own mathematics, with their own AI knowledge, and they do a very good job. And there was no mention of a quantum computer. It was not involved at all. So in some sense, I could maybe think that actually now they started to get separated a little bit more because this AI becomes so powerful. It can do the task of discovering nature by itself, not using quantum mechanics laws, but it did the job. And because the advancements of the discovery of algorithms that could intersect with AI, maybe it's not growing as fast as this like computational power from AI. I could say that temporarily they are not so connected as maybe it used to be described a few years ago, actually.
Interesting. Yeah, linear algebra keeps coming up again and again in a lot of different places. That's what I always tell. I tell my kids this, and I tell anyone like, learn linear algebra, right? You don't have to be really, even if you're not good at it, at least be familiar with some of the concepts, right? Obviously, you want to get good at it, but like it's one of those things where it keeps coming up. And it's also interesting to note a couple of things. One, not that long ago, actually before the pandemic, one of my customers worked at and he was interested in quantum computing, and he had a degree in econometrics, which is also very heavily reliant on linear algebra. And he said something very profound to me that it stuck with me. He goes, well, if you're clever enough, you can turn anything into a linear algebra problem. So I don't know if that's true, but I think that's interesting. And also, too, if you look at how GPUs are structured, they're basically really well designed to do linear algebra. And I think that we've had a number of people, Candace and I have spoken to, that kind of most of them take a dim view to simulating quantum computers on conventional hardware. That being discretely different from quantum inspired algorithms, right? Like this is actually like, I'm going to get a massive, A100 or H100 machine, and I'm going to simulate a quantum computer. A lot of folks are taking a dim view to that. What's your take, and why do you think people are taking kind of a dim view to that sort of approach of simulation?
Yeah, I think it all goes back to understanding like why it is so hard to simulate classical quantum computers. So, the quantum computers are based, the processing of information with quantum, the nature, the laws of quantum, are based on two principles, right? One of them is the fact that superposition exists, which is the fact that you can describe an outcome as a linear combination of two vectors, like the 0 and the 1, but all prefactors multiplying the 0 and 1 are admissible. And it's a continuum, and they're infinite pretty much. And then the other one is the entanglement. So just looking at the first one, which is the fact that you can have a linear combination of two vectors with all admissible values in the prefactors to these two vectors, that makes it like, okay, so if I want to simulate one, like I need 2 and they need to range to take all the values. But if I start to grow the number of qubits, then I need to grow the number of information by 2 to the n, actually. So if it's 10 qubits, it's 2 to the 10. If it's 100 qubits, it's 2 to 100. If it's 1,000, it's 2 to the 1,000. And I need to somehow have enough capacity of computation and storage to be able to describe this very, very large numbers. And some of them can easily grow more than the number of atoms that we have, in Earth and the universe. So it's just that it's a very, I think it probably, if you were to talk to a mathematician, it would tell you that, doing doing computations inspired with working with quantum, there's a very dense problem. It's in the same way that you can have way more dense number of items between 0 and 1 if you were to consider all the real numbers. In comparison, if you were to compare it to all the integer numbers, the amount of items that you find between 0 and 1 is much more larger than all the integer numbers that exist out there. So this has to do with mathematical density of groups, and it's just just not enough. I think it's a very dense problem when you talk about quantum computing and what is available, and the classical information, it's just not possible yet.
I like that. That's a good explanation, because no one's ever really, they just kind of like, nah, you don't want to bother with that. And I think that's a good explanation too. Like there are the number of states or numbers between 0 and 1 is effectively infinite, right? If not infinite, right?
But it's an infinite that infinite is larger than the infinite of integer.
Which is crazy to think about. Yeah. Like, I mean, I had a migraine yesterday, and like just thinking about this, kind of like it either sometimes when I get a migraine and I recover from it, like I can grasp, or even during it, I can grasp some of these things I have with a little bit more clarity. But like, like that's like, wow, I never thought of it that way. It's like, that's pretty wild stuff.
That's an infographic that has to be created.
That is totally an infographic.
It really is.
Yeah.
No, I love that. I love that. So, so let me ask you, what role do you think open source communities are going to play in advancing quantum computing?
So, as far as I understood, so, my education is in physics, and, we do a lot of studies of books and research in the laboratory. But, the work that we do at the university is like, okay, you are in your research group, you publish a paper, and you put it out there. And many other people is trying to do a little bit of similar research, but you want to be the first, and you don't want to be scooped. So it's not. I'm not necessarily sure if it falls under the category of open source, but yeah, what I understand of open source is you have a group of people very motivated. You want to disseminate the information, and everybody gets to contribute equally. And there is not just a person who is keeping all of it. So it seems to me that the fact that at some point the capability of run, for example, on a quantum computer becomes really open to anyone. And the fact that many people with different skill sets, diverse, are trying to solve different problems and from different angles can really make it that we find the applications faster. So rather than only a single group of people, trying to crack the issue. And I think I've seen a little bit of this in the flavor of some companies providing like a big prize for a motivation of a global community of trying to solve a few issues that are outstanding that cannot be resolved just inside. So I think it's very important to give access and that is accessible to many people.
Interesting.
Do you think there is a social impact potential? Like, do you believe that quantum computing can have a tangible social impact, like climate science or medicine, or is that just still like too far off?
Yes, I think the answer is yes and yes. I think it's far, and I think it's possible to have an impact. So we don't know yet, right? We don't know yet when and what is the application going to be. But if it turns out that everything works out and it's a very powerful computer, to do computations, this can be immediately used in pharmacology, in climate sciences, and even without knowing that the problem was solved by a quantum computer, we know that this can help people, right? So yes, there's these fields of pharmacology and climate that will help people. Doesn't matter who solves it. And yes, I think quantum computers at some point will be powerful enough to tackle some of these problems. And by connecting those two is how we will benefit from quantum computers in the future, actually.
Interesting. Yeah, no, I think one of the big problems I think we have when it comes to climate, right, I'm a big fan of solar, right? I even built a little solar generator. But if you look at the pricing of solar systems now, even if it's just the camping, like small kind of stuff, the cost of the panels are actually trivial now, right? Or almost trivial, right? It's the battery, the storage mechanism and the chemical, if we had a better way to simulate kind of like what chemical concoctions could store energy, we would solve a lot of that problems. I mean, for many years, and also I think there's also room for improvement in the efficiency of solar panels too. But yeah, I mean, like in terms of just that alone would go a long way. I think the advantages of what quantum computing can do in material science will go a long way to improving like societal impact and things like that. And I think now you can argue now that even with kind of annealing type systems, you can get optimization of delivery routes and things like that. You can kind of, I mean, obviously it's not, you can reduce the amount of emissions and whatnot, and based on optimization. I think you can kind of get some of that now, but I think the best is yet to come.
Yeah, I agree. We have a lot to wait for, and
right.
I'm a little bit both optimistic and not so optimistic. I do hope it happens before it's my time to pass.
Right.
I really would like to see it.
You're in a superposition of optimism.
Yes.
And pessimism. Right?
Exactly.
The glass is both half full and half empty at the same time.
Right.
Yeah.
So
yeah.
No, I think that I mean, I also think too, a lot of people are. Again, I live in the DC metro area, right? So obviously I'm going to think more, in terms of, national security, kind of defense tech stuff than the average person, just because there's just so many people around me are in that industry. I think everybody is freaking out about Shor's algorithm, and that's probably going to be one of the first dominoes to go, or problems to be addressed, because there's a lot of money and a lot of a lot of national willpower behind getting that sorted out. But beyond that, so do you think it'll take like more qubits to see? Because there's a number of debates about a number of usable qubits. I probably should put that in air quotes, usable qubits. Their protein folding, I think, will take more. Some of the more material sciencey stuff is going to take more than what it'll take to break RSA. That's the impression I get. I could be wrong, because one of the things that's fascinating about this space, every time I think I got my head around something or I got a handle on something, no, it's actually not the case.
Totally
Or it's like, what? Like what?
We learn something new every episode. Every
Literally.
episode, at least, I mean, and more than one thing we learn every episode. But really, it just, whenever I think I've got a handle on something, and then we meet somebody and they say something, and I'm like, I have no idea I don't know.
Right.
I don't know again, all of a sudden, and I've got to really understand it's so expansive. Sorry. I had to agree. I had to agree. Well, and that's what's really beautiful about the role of curiosity, right? Like Frank said, I'm wickedly curious, and I've always been that way. I don't come from a tech background. I come from my father was an IBM inventor. He was a quantum physicist back in the 80s, the 70s, the 80s, and the early 90s. Like he was always like literally like writing algorithms. I mean, I had no idea what he was doing as a kid. Like I'm 8 and I'm 10, and I can't tell anybody at school what my daddy does because I don't understand it at all, right? And he's like writing algorithms. Like he was so far ahead, of what was going on. But it tickled my interest that my whole life I've been running towards technology. And now I'm like running full steam at quantum because again, it really suits my type of curiosity. So what's something that you're still curious about in quantum, even after all your learning and your experience?
Yeah. Something that I face quite often when I work with customers and they start to connect their application to what we offer at Quantum Machines. It usually starts with doing some preliminary measurements and then doing calibrations. We do calibrations of their qubits, and then once that's completed and you agree that it has reached some level of calibration, then you start to work on the algorithmic part, whether it's simple or complex. So a lot of the things that I face these days are calibrations, because it's the initial stage before everything, all the magic starts, you could say. And I always wonder, I work with a customer, I do it once. I work with another customer, I do it slightly different. I work with the next customer, and then it's a different qubit type, and then it's a slightly different. It actually, a big curiosity that I have is like, what does it take from the hardware and the hardware physicists, the hardware engineers, for us to achieve like the best calibrations that we can achieve. And that is in two questions. It's like, what is the quality of the receiving end, the quality of the qubits, like how much good they need to be to achieve the calibrations. And then the second is like the operations and the routines of calibration. So I wonder, how can we make it so that, okay, it's a little bit better? How can we make it so that you get a little bit better of fidelity, which is like a parameter of calibration? And that's something that keeps circling on my brain. Like I wonder, like we have a protocol, for example, resonator spectroscopy versus amplitude, and then I wonder if can we do it differently? Can we write it in a slightly different ways? Can it save more resources? Can it lead you to the answer faster? So these are questions that keep circling on my brain a lot, I would say. And it's not about the quantum application yet, because my role leads me to be closer to the hardware layer, so not too much to the algorithmic layer. And where I'm sitting, this is one of the topics that I think the most, I would say.
Interesting.
That's exciting.
Thank you.
I want to ask you about mentorship, because I think it's really important. Have you had a mentor in this space, or have you mentored others? how important is community in learning quantum?
Yes. I think I have had mentors. I haven't, whenever I thought and I said to myself, oh, I need a mentor, actually it didn't really lead me too much anywhere. Because when I was trying to be conscious about it, but when it happened just by chance or by coincidence or by a conversation, and in retrospective, I can call it that I received mentoring, then it is when it worked actually. So and I'm looking back even beyond quantum computing, right? I'm talking way back from like undergrad and grad school. So there are two things that are important for me. One of them is receiving the information that is not obvious from the mentor. What I mean is that, the mentor, not necessarily older person, but maybe more exposed to the field that you want to be at. So they know some insights that are difficult to get when you're from outside, right? So, getting that information, passing it and making it available, that's something that what I think mentorship is about. And, disseminating this so that you can quickly catch up to speed and know where to start. That's great application of mentoring. And the other one is a little bit in the community is, by the mere fact of finding a person that has some characteristics or connection to you, whether it's culture, gender, or type of studies or nationality, all of that just happens you to encourage and understand that it's feasible. And once you understand that it's feasible, that's when the barriers just, when the gates open pretty much. Once you understand that you're not limited because someone else did it, that's when the psychological barrier of like, I can do it, it starts. Like the barrier removes and you can start, and then you start to find ways to get there, even though nobody told you how to get there actually. Yeah. So it's really important.
That's
Okay.
cool. Awesome.
Mhm.
So we're just want to be respectful of your time. We could talk for
Mhm.
another hour. But where can folks find out more about you, what you're up to, and your company?
Yes. So the profile that I keep is my LinkedIn profile. That's where usually people can find about the recent things that I am participating on, and in relation to either my personal life or my professional work. That's a little bit about myself, and then I work for Quantum Machines. Our website is quantum-machines.co, and our we really want to accelerate the era of quantum computer. That's what we're all for, and we do it in a slightly different ways, and we do it through our products and our interactions with our customers. So people can find me at events like March Meeting. It's a American Physical Society meeting. It's mainly for academics, but that's where people will find me. And if I'm working, I work with a lot of customers in everywhere. So I happen to be in universities or different cities. And if you happen to know someone who has a quantum machines product, you can probably ask for my name and see if I'm around.
That's cool.
Yes.
That's cool.
Yes.
The industry's still small enough where you could do that, right?
Yes. Yes, it's a not so large community.
It really is, because I attended my first quantum in-person event like ever back in, was it May, Candace?
That's
I
right.
forget.
That's right.
It was May, and like I would, introduce myself, and they would either know who we were, or, which was cool,
Yeah.
or they'd be like, you should talk to so and so, and I'm like, oh, I know so and so. Like it was like it had that kind of that weird, like a small town feel, which you don't really get. You know, you don't get as much in AI anymore, like you did like maybe 10 years ago, or even just kind of, .NET development, which you did 20 years ago, right? Like it's kind of nice so to have that close-knit community, which
Yes.
I know at some point that'll probably go away, but it is nice to have that again, So cool.
Yes.
Any parting thoughts, Candace?
I really appreciate this. I appreciated especially how you shared your curiosity, and told us even more that we have to investigate. I 100% want to have you back, to ask you
Thank you. That
even
would
more
be lovely.
questions.
Yeah,
That's
absolutely.
excellent. Oh, it's been a wonderful time, and I thank you so much for your time. I really do.
I really
Thank you very
appreciate the
much.
time that we talked to you, and it was a lot of fun. I really enjoyed it. It was very comfortable. Thank you.
Thank you
Wonderful.
very much. And we appreciate that. And we'll let our AI finish the show.
And there we have it, dear listeners, a delightful detour through the weird and wonderful world of quantum computing with the ever-articulate Kevin Villegas Rosales from Quantum Machines. From calibrating qubits to pondering quantum machine learning, Kevin reminded us that success in this space doesn't hinge on mysticism or magic, just a healthy dose of physics, curiosity, and the occasional existential crisis about linear algebra. Whether you're deep in the science or just here for the t-shirts and buzzwords, we hope you found some clarity amid the entanglement. And if not, well, perhaps you're just in a superposition of understanding and confusion. Perfectly normal. Big thanks to Kevin, to our brilliant co-hosts Frank and Candace, and to you, yes you, for joining us on this quantum ramble. Don't forget to like, subscribe, and teleport this episode to a friend using whatever spooky action at a distance app the kids are using these days. Until next time, stay curious, question the noise. And remember, in quantum, as in life, nothing is truly certain, except maybe that we'll be back with more. This has been Impact Quantum. I'm Bailey, signing off, but never fully collapsed.